Welcome back again to my lecture on discrete mathematics, and today the first part here we talk about the number theory. What is the number theory? Well, number theory has a wide range, but today we are just going to deal with some of the basics that you have already studied in your high school. Let's start with the famous number, the prime number. And why do we need prime? That's one of the most important questions. And you'll be surprised how primes are being used, and you will be surprised to know that there are still research going on this prime numbers. As I told you, prime numbers are quite unique and they are not well understood. So it acts as a basis for today's cryptography as well. And in our lecture here we usually talk about the positive integers. So we are going to deal with various aspects of prime numbers initially, and then we are going to talk about the LCM and GCD of the numbers. Let's start with the basic operators like a divides operator. So in notion of 3 divides 12, we use a symbol just like a straight line, 3, and there is a straight line, and then 12. So this can be read as 3 divides 12. To specify an integer evenly divides another integer, we use this symbol. And as we progressed from previous lectures, and even in coming lectures, we will be introducing various symbols along the discrete mathematics course. So try to get along these symbols, because later on somewhere when you are in any other courses, either that deals with image processing or cryptography or graph theory, at times you will come across these notions, so you would be able to get what it means. Well, coming back to this point on the divides operator, we do have not divides operator. As we can see here, this supposed to be like this, phi not divides 12. So there is a typo there. Well, to specify when an integer does not evenly divide another integer, we use this operator here. So the above operator, phi does not divides 12. Let's go on and see few more points back to this theorem on divides operator. So if A divides B and A divides C, then A divides B plus C. What do you think? Well, you might have come across this in the high school. Let's see some examples. Yes, if phi divides 25 and if phi divides 30, then phi divides 25 plus 30. That's a simple example that you have to prove that theorem above. And if A divides B, then A divides B times C for all integers C. Well, that makes sense. As you can see, we have the C as an integer, though we don't know what is C, but we are sure that A would divide B times C. So here is another example here. If phi divides 25, then phi divides 25 times C as well for all integers C. Well, that seems to be very basic thought on this divides theorem. And this is a kind of interesting point again. If A divides B and if B divides C, then A divides C. Does it sounds like hypothetical syllogism? Later on we will talk about another relations. It's about transitivity. And also if you go back to this proposition functions, we also talked about similar things like syllogism. If A implies B and if B implies C, then A implies C. It's something like if A is equal to B and B is equal to C, then A is equal to C. But in this part of divides operator, the operator itself is quite different, divides. So if A divides B and B divides C, then A divides C. That's what we talk about. Well, in this example we can see 5 divides 25 and 25 divides 100, then 5 divides 100. Well, with this thought, let's move on to this prime numbers again. Let's start with the basic forms of definitions. The positive integer p is prime if the only positive factors of p are 1 and p. Well, that's the very famous definition of prime numbers. We know that if there is other factors, that becomes a composite number. Moreover, note that 1 is not a prime. 1 has its unique features. Yeah, it has a unique class. It's not a composite number either. So an integer n is composite if and only if there exists an integer a such that a divides n and a lies between 1 and n. So basically I want to introduce this prime numbers and composite numbers, then later on we will move on with some of the basic theorems behind these two numbers, as well as we will talk about LCM and GCD. So the fundamental theorem of arithmetic defines this way: every positive integer greater than 1 can be uniquely written as a prime or as the product of two or more primes where the prime factors are written in order of non-decreasing size. So it's one of the famous fundamental theorem of arithmetic. Note that here every positive integer greater than 1 can be uniquely written as a prime or as the product of two or more primes. Isn't that interesting? Let's see how it applies. So we have 100. 100 is not a prime number, but this 100 can be written as a product of two or more primes. Yes, you can see here 2 times 2 times 5 times 5. Right. Then you have 182. Well, that's obviously not a prime number. And you can see here 2 times 7 times 13 as 2, 7, 13 are prime numbers. These product of these prime numbers bring out the number 182. And we'll go further of like 29,820. Still that can be written as the product of prime. 2 times 2 times 3 times 5 times 7 times 71. Yes, this is one of the fundamental theorem that we have to keep in mind. So if n is a composite integer, let's talk about composite factors now. If n is a composite integer, then n has a prime divisor less than or equal to the square root of n. So that's an interesting observation, and we can use that in fact to show whether a number is prime or not. So it says that if n is a composite integer, then n has a prime divisor less than or equal to the square root of n. Let's see how this applies. Actually, here we can simply look at some strong inductive proof using following logics, and don't get confused with what is strong inductive proof. Well, in our coming lectures we will talk about what is inductive proof, as well as what is a weak inductive and what is a strong inductive. For the time being, for your reference, we will see some logics here. If n is a composite, it has a factor a such that a lies between 1 and n, and thus n equals a times b, where a and b are positive integers greater than 1. In that case, either a is less than or equal to root n, or b is less than or equal to root n. Otherwise, a times b is greater than root n times root n, that is greater than n. Thus n has a divisor not exceeding root n. With this thought, we can see this divisor is either prime or a composite. So if it is a composite, then it has a prime factor. That is the point. If n is a composite integer, then n has a prime divisor less than or equal to the square root of n. So in either case, n has a prime factor less than root n. That is the point here. Let us consider some examples and see how it applies. Show that 113 is prime. So what is your method of finding a prime? Well, we have many different methods to identify whether a number is prime or not. So here is what we are going to do. We are just going to follow this composite algorithm or composite theorem, which we just saw in the previous slides. Let us see, just take root of this number, that is 113, and root of this number is 10.63, and try to see what are the prime factors less than 10.63. So the only prime factors less than root of 113, that is less than 10.63, or 2, 3, 5 and 7. So suppose either of these divides 113 evenly, if suppose 2 or 3 or 5 or 7, if any of these prime factors divides 113 evenly, then it is not a prime number. If it does not, then it must be a prime number. That is the idea. Let us consider this 899. Try to show that 899 is a prime. Why don't you take a moment and try to solve it? How do we do that? Take a root of 899 and see what it is. It is 29.98 is that is the root of 899, and now try to see all the prime numbers that are less than 29.898. So when you find prime numbers that are less than 29.98, we start with 2, 3, 5, 7, 13 and so on, and of course we do have 29 is less than 29.98, and we find that 29 divides 899. So in that case, this 899 is not a prime number. So then we have this famous theorem on primes, the theorem by Euclid. There are infinitely many prime numbers. How do we know? Let us try by proof by contradiction. Assume there are finite number of primes, and we have to prove that there is infinitely many primes. So list them as P1, P2, P3 till Pn. Consider the number Q as P1, P2, P3 till Pn plus 1. So we have this two parts. So this number is not divisible by any of the listed prime. So this, if we divide Pi into Q, that would result a remainder of 1. In other words, we were not able to divide this number Q. So we must conclude that Q is a prime number, not among the prime listed above. Consider the list. Initially we had a list P1, P2, P3 till Pn, and now we are considering a number q which is not in the list. This number q is not listed as the prime number. And now what we are going to do is that we are going to divide p1 into q, and we know that any numbers can be divided by prime or product of primes as the factor with any numbers. If it has a factor, then it is not a prime, but here we find that this would result in a remainder of 1, which means that we can't divide. So therefore we could conclude this number q is a prime that is not among the listed prime above. So this contradicts our assumption that all primes are in the list. Therefore we can surely say that there are numbers that is not in the list, and eventually it has infinitely many prime. So prime number theorem, again, the ratio of number of primes not listed or not exceeding x, and x divides the natural log of x approaches 1 as x grows without bound. So that might seem complicated. Let's simplify it with rephrasing. The number of prime numbers less than x is approximately x by natural log of x. So the chance of a number x being prime is 1 by natural log of x. So let's consider what is the chance of a 200-digit prime number, 200-digit number to be prime, you could say that. Consider you are trying to find a number which is 200 digits and you want to know whether it's a prime or not. And suppose you already have a number which is already 200 digits and it is a prime number. How do we find that has to be prime? The question is, two questions I have in hand. One is, we have a number, 200-digit number, and you want to find whether this number is prime or not, and you can see that the chances of a number x being a prime is 1 by log x. So you can see the probability or the bound that grows in finding the prime numbers. So it's the natural log of 10 power 200, approximately 460. The chance of 200-digit being prime is 1 by 460. So if we only choose odd numbers, because even numbers are not a prime number, so let's just choose odd numbers, then we have 1 by 230. So this result we will be discussing later on, because we will see the computation complexity of finding a prime is quite expensive. We will talk about it later on in this lecture. So just for your reference, I want to show you the complexity, computation complexity of finding a prime, or chances that a number is being a prime. And eventually these days we use computing technology to compute these prime numbers. Showing a number is prime or not. Consider showing that 2 power 650 minus 1 is prime. That number is about 200 digits. Yeah, in the last slide we talked about 200-digit prime. So approximately 10 power 193 prime numbers less than 2 power 650 minus 1. So this theorem that we just saw, by that method we can see that x equals 2 power 650 minus 1. And how long does it take to test each of these prime numbers? Well, let's assume that we have a computer that can do 1 billion flops per second, or if you even have computers that can do 1 billion operations per second. That's quite fast enough as well. Of course, these days we do have such computing facilities with GPUs coming in. So here in this case, it would take 10 power 193 by 10 power 9, that is equals 10 power 184 seconds. Well, it's in seconds. Does it sound less? If you convert that seconds into years, it's like 3.2 times 10 power 176 years. Can you imagine that? That's quite a lot of year we can't comprehend, because we know that even if you think about 10,000 years before, or even for that matter 5,000 years before, the human, we didn't have any such computing mechanisms, and we know that results of all those 5,000 years. So we can't go back beyond that. So here we talk about computing just a 200-digit prime number. If you want to test each of these primes, then it takes 3.2 times 10 power 176 years. That's too much. Of course, there are quicker method to show the number is prime. Let's go further. We will be using it later on at some stage. Division algorithm. Well, let's see. Let A be an integer and D be a positive integer. Then there are unique integers Q and R, with R lies between 0 and D, such that A equals DQ plus R. Well, with this we can see that we have two operators. Q equals A divides D and R equals A mod D. So modulus operators. Greatest common divisor. A greatest common divisor of two integers A and B is the largest integer D, such that D divides A and D divides B. Well, we'll consider an example. You will right away understand what it is. So greatest common divisor, we simply call it as GCD. Let's see an example of this. GCD equals GCD of 24 and 36 equals 12. So how do we find it? GCD is the greatest common divisor of two integers. So our two integers here are 24 and 36. So for 24, the greatest common divisors that 24 and 36 has, let's see, or say for example it divides by 2, 3, 4, of course 6 as well, and 12 and 24. So we want to see which is the greatest common divisor for these two integers. So as you can see, this is the greatest common divisor. Of course 2, 3, 4, 6 are common divisor, but they are not the greatest. 12 is the greatest. So that's why here in this example we have 12. Likewise, the greatest common divisor for 17 and 22, it's 1. There is no other common divisor. Of course, we do have 1 here as well. Well, with this thought, you can see, you can calculate any GCD. For 117, still you have 1 as the greatest common divisor. Relative primes. What is relative prime? Two numbers are relatively prime if they don't have any common factors other than 1. We saw an example just now. So let's say A and B are relatively prime if GCD of A comma B is 1. So we know that GCD of 25 and 39 is 1. So 25 and 39 are relatively prime. Let's see more on GCD. So here is the two numbers of A and B, and we can rereturn A and B in this form. And let's see if you can see what is the GCD of 120 and 500. So this is a kind of a shortcut where we use the prime numbers like 2, 3, 5 and its power to evaluate the given GCD. So GCD let's express 120 and 500 in terms of this form, then compute the GCD using this following formula. So the basic thought is simply we are trying to use the same notion there. Okay, that's the same notions that has been applied here as well. So with this thought in mind, you can see a GCD of 120 and 500 comes to be 20. Least common multiple, it's another term. The least common multiple of a positive integer a and b is the smallest positive integer that is divisible by both a and b. Let's see, we denote it by LCM of a comma b. So we can use this form similar to the GCD form that we had earlier, LCM of a comma b. So LCM of 10 and 25 would be 50. That would be the least common multiple that you have in hand. So likewise, you can still find LCM of larger numbers. For example, here we have a very large number, 95,256 and 432. So we can use this form to identify what would be the best results. So it's a shortcut by which you can find the LCM, and LCM turns out to be 190,512. So that's a simple way of finding the least common multiple. So these two LCM and GCD theorems, a and b be positive integers, then a times b is GCD of a comma b times LCM of a comma b. So let's see here, GCD of 10 comma 25 is 5 and LCM of 10 comma 25 is 50. So 10 times 25 equals 5 times 50. So do you see a relation there? Yes. So you can take a larger example in which you have GCD of those two numbers, like larger numbers, 95,256 comma 431, GCD of that and LCM of that. You can actually reveal we have a relationship developed during the course of time. We have come up with LCM and GCD theorems. Well, today we talked about various features of number theory. There are a few more things remaining in this part which we will consider in the coming lectures. So as we get familiar with these terms, just brushing your knowledge that you gained during your high school math, let's move on into this discrete mathematics with these basics ahead. Until then, see you again. Have a nice time and goodbye.